Okay, hello everyone. My name is Vladimir Gladshtein, and I'm going to present you our paper, Mechanised Hypersafety Proofs about Structured Data. Well, we deal with data a lot nowadays, and usually this data comes in some sort of structure. For example, if we talk about images, then the data representing images can usually have replicated values. If we talk about symmetric plots, the data representing symmetric plots can usually be symmetric as well. And then for graphs and networks, this data can be sparse. Then we can exploit this structure to compress our data. For example, if we talk about matrices with replicated values, we can simply compress them by just storing each unique value with number of times it repeats. Then for symmetric matrices, of course, we can just store the upper triangular. And then for sparse matrices, where only a few elements are non-zero, we can easily compress them by storing non-zero elements with some metadata, which allows us to reconstruct the whole matrix. And the story doesn't end here. At this PLDI, we have one workshop, one keynote, and also at least 4 papers, excluding the one I'm presenting, which are related to computations on structured data. Well, those computations, they can actually get very tricky. So there's the code that sums up 2 non-compressed matrices. You can see it over here. And if you have sparse matrices which you compress, then the code to sum them up gets way more complicated. So then in our work, we try to answer the following question: how to verify general computations on structured data. More specifically, let me tell you what exactly do we want to verify. So imagine you have some data or a bunch of different datas, and it is like structured vector, matrix, or tensor, and you compress it somehow. Also, you have a pure mathematical operation star, which you want to compute on this data. So you want to ensure that given some computation on the compressed data x, this computation exactly implements this pure operation star as we were computing it on the decompressed counterpart of x. That is our goal, and we will build a verification framework which allows for 3 things. First, we want concise specifications. Second, succinct proofs. And finally, we want to account for general structured data. So we present LGTM, which stands for Logic for Graceful Tensor Manipulation. And now I will show you how to specify and verify computation on structured data using our logic. Of course, first of all, we will focus on the specification, which is going to be hypersafety in this case, and let me explain you why in a minute. So as the running example, we will be looking at the very simple computation, which is the product of the sparse compressed vector and the dense vector, non-compressed one. And we will compress our sparse vector using 2 arrays. First one is xval, where we store only non-zero elements. And the second one is xint, where we store indices of those non-zero elements. And that is called sparse vector format, where format stands just for the compression strategy. And then we have a dense vector, which means that this vector is not compressed. So if we want to take a dot product, we will have to just iterate through all non-zero elements in our compressed vector and multiply them by correspondent element of the dense vector v, and then sum up the result. So that's the code, SPV, which exactly implements this. And we want to ensure this code exactly implements this pure mathematical operation, right, which is you can see on the screen as well. And now to construct our specification, we only have to understand how do we represent formats. More specifically, in this case, how do we represent those 2 vectors. And the traditional approach would be to represent them as predicates. If we do like that, then our specification looks as follows. So let me explain it a little bit. Well, for the dense vector, it's fairly easy to represent it. We just use the standard predicate for arrays, where we say that, well, we have array v with some pure payload. But then for the compressed vector, we will have to come up with a specific predicate sv, which says that, well, x is some array, right, not our array that we are working with, and it is encoded with 2 other arrays, xint and xval. So if we do as follows, then we can say, well, after running SPV, the result is going to be a pointer ends, which exactly points to the dot product written as the pure mathematical operation. And this approach was taken by the following work, where they present LA proof framework. And authors, as the part of this work, they verify the dot product of the matrix compressed with the CSR format. You don't have to know what is that. and dense vector. Well, the representation of this basic CSR compression format as the separation logic predicate looks like this. And if you want to understand what does it mean, you of course have to be you of course need some expertise in separation logic. Also, it follows by 350 lines of format-specific lemmas. And in our work, we neither want to come up with predicates for each particular format, nor write hundreds of lines of code for each particular format and the proof. So what we do instead we analyze a bunch of libraries for sparse data computations to understand how programmers represent those formats themselves. What we found is that for each particular format, programmers implement so-called getter function. And getters functions, they retrieve the value at the given location. Moreover, for the modern compiler, for sparse and structured data, they also represent formats as something which can be interpreted as getter function. And now, in this specific case of sparse vector, this getter function, it will take the encoding of this vector and also the index I. It will try to retrieve the element of the sparse vector by this index. More specifically, in this case, it will iterate through all indices of all non-zero elements of our vector, and it will try to find I among them. If it manages to do so, we will return the correspondent element of X-wall array. Otherwise, we will return the default element, which is 0. And that is the first key idea of our work. We represent formats not as predicates, but as code, because then we can handle general types of structured data. But the question is, can we actually prove something if we represent formats as code? And in order to give you intuition about that, let's switch to a slightly different example for a second, which is the dot product of two compressed sparse vectors. Imagine you have two compressed sparse vectors, x and y, and you want to implement the dot product. So here's the code for dot product. You don't really have to understand what exactly is happening over there. But one thing to note is that if you represent getters as simple imperative loops, then the loop in this product code would be just the composite of those loops. So let me explain you why is it so. The idea is that each getter tells you how to traverse your data structure individually, And then the code for product will use this information to construct the simultaneous traversal of all data structures which are involved in the computation. Well, so that's not surprised that optimized computation will incorporate getter's code. And then we will try to facilitate our proofs in the relational manner by relating the correspondent parts of getters with their counterparts in the product code. All right, so let's get back to our example, and let's see how we specify. I will run an example representing formats as code. That is our old specification, and we want to get rid of this SV predicate. Well, we still have to assert that xInd and xwal are arrays, so we will assert them as follows and abbreviate it with ars predicate. Now, remember that the getters are just imperative functions, which means that if we want to interpret it in our specification, they should go to the code section. Well, the question is how. And to understand how exactly are we incorporating them into our specification, let's look at those xi's. So those xi's are now unspecified components of the compressed vector. Well, also this summation actually mentions all of them from 0 up to n-1, which means that if we want to capture all of them, we will also have to run all the getters on all indices from 0 up to n-1 as well. And that is the triple. Well, let me try to explain what does this triple mean. First of all, note that this is a hypersafety specification triple in the sense that it states some property which relates outputs of many programs. Well, here we have a bunch of programs which run independently. One of them is SPV, the code for our dot product, and other ones are just getters. We run all of them independently on distinct memory heaps, each of which, for each of which we assert ars predicate, and also each of which is indexed by some index corresponding to the program. Well, now each getter will give you the correspondent value of the compressed vector, and then we just bind all of them to particular xi variable. Well, now we can use those xi variables to represent our vector x and specify the dot product. Well, that's the rough meaning of this triple. And also note that the size of this triple is n+1, where n is the size of the input data, which means that n is a parameter. So our triple is parametrized. The size of the triple depends on the input. And LGTM is the first hyperlogic which deals with parametrized triples. Now we finally come to the second key idea of our work, key contribution of our work, which is the set of principles to deal with such parametrized triples. And I will try to show you how this parametricity allows us to streamline proofs about loops and about such code in general. Well, so now we will prove this triple, but before we even start proving, let me introduce some notation just to make this triple a little bit simpler. Well, we have these parameterized components, and instead of writing all those getters one by one, we will actually collapse them into a single line, where we mention the general pattern of the index to I, and also we mention the set where I iterates over. In this case, that's all indices from 0 up to n-1. Also, we will have the following shortcut, where we say that R's predicate is just asserted in all distinct memory heaps. Finally, we assemble all the outputs of all getters into one vector x, which represents our compressed vector, and which we then use in the post condition to specify the dot product. OK, that is our triple. Let's try to prove it. The first step in this proof would be to get rid of all getters, which give us 0. So we will focus at this component of the triple, and we will split it into two. The first one is just those getters that give us non-zero, so those getters that we run inside xint array. And the second one are getters which we run outside of xint array, which means that they will just give us 0, right? And then that means that this part of summation, we can just replace it with 0. Using the focus rule of LGTM, we can reduce the triple above to the one where we only focus on non-zero getters. That is the triple that we have now. And in this triple, we only consider getters which are run on indices from xint array. Now, remember that SPV is just a loop, which we also run on indices of xint array. It's over there. So we can represent it as a number of iterations of its body. And then it has the same number of iterations as we have getters, right? So, which means that the parameterized component of the triple exactly matches the loop structure. Moreover, the ith iteration of the triple exactly processes the output of the ith getter over here. So then the rule for the for loop in our logic allows us to pair the ith iteration of the loop with the correspondent run of getter. And then we can reduce our triple to the following one, where we only have to ensure that the sum that ans accumulates will be increased by one more element of xint array. And this triple has now only two programs, which means that we can dispatch it using regular relational logic methods. So I will omit the rest of the proof in this presentation. Well, now I have shown you that hypersafety allows us to encode formats as code, and also parametricity allows us to streamline proofs and match these loop iterations with our getters. So this actually can help us to prove, to verify computational structured data. Now let's talk about evaluation. So what about numbers? To evaluate our approach, we implemented it as the COG framework on top of CFML. And we wanted to know if our proofs are short, and also how do they compare to previous approaches where they use non-relational logics. What we did, we verified 13 characteristic examples, and some of them are actually quite complicated kernels, like sparse vector multiplication, and then sparse matrix sparse vector multiplication, and also we have alpha blending here. So in average, our proof code ratio was just 2.55, which means that, well, our proof is not than 3 times bigger than the code in average. And also, we verified this example from the previous works, which is the matrix compressed with the CSR format times dense vector, and our proof was just 36 lines of code, which makes it more than 10 times shorter than the proof from the previous approach when they use unary logic. Well, that's it. In this presentation, I wanted to show you that actually hypersafety is good for specifying computations on compressed structured data. Then I wanted to show you that parametrized ripples can also help us to streamline proofs about loops, for example, and other stuff that we meet in such computations. And finally, I have shown you that this approach can lead us to, at most, to up to 10x reduction in proof sizes compared to unary logic approaches. Yeah, thank you very much. Our paper and code are available by these QR codes. We'll be happy to take your questions.
So you showed us how you can take some code that programmers would write anyway and use it as a specification. You chose getter functions. I might have first guessed that a generator of all the positions within a data structure would be both natural and maybe make some of the reasoning easier. Did you consider that alternative?
Yeah, thank you very much for the question. That's a very good question. And so there is one, we tried this as well. And there is one disadvantage in representing formats as the code that kind of decompresses the matrix, right? The problem is that this loop, for example, this code will have some kind of loop. And sometimes this loop actually has different structure from what the optimized implementation will do. So it can skip some elements, or it can traverse some elements in different order, and then you will end up with some sort of loop alignment which will be really difficult to justify. For example, you can see here that in order to align the SPVV with all those getters, we had to first run those getters which we run on all indices outside of X in the array. So which means that if there was a single loop, we had to take out those iterations first, and then we will have to show that all these getters are independent, and show that this permutation actually can be done in this particular case. So if we represent formats as the set of independent runs, we can split them in the way we want and permute them in the way we want. That's why we can have this benefit of short proofs.
Thanks.
Thank you.
Hi, very nice talk and great paper. Thank you. So one question I have is that in the LA proof paper, one of the main ideas is to connect these proofs about the correctness of, for example, the sparse matrix vector multiplication to accuracy proofs about floating point arithmetic. Mm-hmm. And so there are some complications, like you're saying the 350-line proof has to deal with things like multiplying by 0 and floating point and so on, which is not always 0, as it turns out. And so I wonder if we wanted to extend the proofs that you have to encapsulate also these proofs about the accuracy of floating point. What do you think would need to be done? How many additional lines of code? Like, is it possible in your opinion?
Thank you for this question.
Yeah.
And the thing is that this computation, so all 12 examples until like the 13th one that we verified were using integer valued matrices. But then the 13th one actually deals with floating point numbers as well. So I guess in this work you have kind of some separate library for accuracy proofs, and also then you have some library for where you actually verify this computation, right? So and then, we also verify it with floating points, and then you can just use this library for accuracy independently, I guess.
Okay. But specifically, maybe it's a small point, but like the 0 times something not being 0, that's like a property that you use in your proofs or no?
We account for that. So we have, so our proof accounts for that, and then we also have, I guess, this f-eq, right? Predicate which says that two numbers are equivalent in terms of so now in here we say that result is this f-eq to
great. Cool.
to what you expect.
Yeah, thank you.
Let's take one last brief question while the next speaker sets up.
Yes.
Okay, yeah, thanks for the talk. That's a cool Hoare triple with a lot of code in them. I was wondering, what does it look like to use such a Hoare triple in my own code? Like I have some code that has a bunch of vectors and matrices, and now I'm calling the function. Obviously, I'm only calling the function. I'm not also calling the 1500 getters at the same time. So how do I take this big thing into something unary I can use in my remaining reasoning?
So the idea here is that you have, like, in this big triple, you usually have some constant number of different programs, right? So all those getters, they usually have this, like, they are the same, right? Or you can have more getters which would be the same. So you can have just like some 3 or 4, maybe, okay, depending on how many tensors you have, you will have some constant number of, not parametrized number of like same programs. And then usually you just execute all of them. Like, you don't execute different programs in one step. So usually only execute like the bunch of similar programs in one step, and we have rules for that allows you to kind of execute them, like interleave them and execute them one by one. But we also can take this question offline, so we can.
Okay, yeah, I'd love to see more about that. Thanks.
All right, let's thanks to speaker again.
I figured that.